Hi gents, just sifting through the requests. This one came up as a question from our samples that I gave you. This is sample one, I think it is. Does it say educate.ie sample one, paper one? So obviously people are working their way through this, which is good to see. This question's on limits, and that is nice. Thanks, Ronan. This is on limits, which we've sort of done already in a previous one, but not ones quite like this. So worth just reminding ourselves how to do this particular one here. Okay, we've got the limit as n goes to infinity of this thing here. So the first thing I would try to do is I would try to see, well, what happens if I do place in infinity into this thing here. Okay, if we do that, we just see the top becomes huge and the bottom becomes huge, and it is not clear what's going to win as we do it. So there's a couple of ways that you can go about this. The way that they would like you to do it is they would like you to divide top and bottom by whatever the highest power of n is. In this case, if there was n cubed, we divide top and bottom by n cubed. In this case, just n to the power of 1 is the highest thing that we have. But if we did have higher, that is what we would do. So we're going to say it's still the limit. We haven't done anything to it of infinity. And what we're going to do is we're just going to divide top and bottom by n. So if you divide the top by n, just get 2. Divide the bottom by n, you get 3 plus 4 over n. And now it becomes more obvious what happens when we make n really, really large. You're going to have 4 over something gigantic that's going to start heading towards 0. So the limit is simply 2/3. You can cheat a little bit. You can put in a gigantically big number in for n and see what's it kind of close to and work it out from that. But this is the way to do it. And of course, there's also L'Hopital's rule. L'Hopital's rule says if you just place in the number and you get infinity over infinity or 0 over 0, this is going to be useful when you go to college. What you're entitled to is you're entitled to differentiate the top, differentiate the bottom. So if we do the limit as n goes to infinity, well, just check, we do get infinity over infinity, we do. You differentiate the top, you get 2, differentiate the bottom, you get 3 plus nothing. You just get the limit of 2/3 as n goes to infinity. N can do whatever it wants, it's not involved in it. The answer is 2/3. Okay, that's a nice little one here. Maybe in this case you're not really saving much there, but there are other questions where that is going to be absolutely fantastic to use. Okay, the limit of 2 times 1 third to the power of n, again as n goes to infinity. Really, you just have to just think about this one here, okay? When you do a third by a third by a third, it's getting smaller every time. As you do it infinitely, it's heading towards 0. So we're going to end up with 2 amounts of 0, so its limit is 0. It's heading towards 0 again. Feel free just to throw in a gigantic number there. You'll start seeing it's headed towards that. Now this thing here, 1/3 of 2 to the power of n as n heads to something gigantic. Well, 2 to the power of something gigantic is colossal. And just because you're dividing it by 3, it's still going to be colossal. So as this gets, as n gets bigger, the whole thing gets bigger, and it heads towards infinity. Okay, prove s to the power, or sorry, s of n is equal to a times. Okay, well this was actually something that we did in a previous video, but not doing it by induction. So we're really finding this formula in lots of different ways, just trying to show that this thing is true here. Okay. For the sequence of partial sums of a geometric series. Okay, so what we want to do here is we want to just first of all let n equal to 0. So what we get is we get s1 is equal to a times 1 minus or to the power of 1 over 1 minus or. So we try to see, is this correct? And it is correct. We end up getting that S is equal to A. So S1 is equal to A, we should say it like that. So we know that when we're adding up the sum of the first however many things, we know that that is going to be the first thing that we get. So you know what, actually, I shouldn't write it like this. I think the way that I should write it is this. The left-hand side is A plus A or plus A or squared plus dot dot dot, because it is a geometric sequence, plus A or, now what does it finish with? Okay, what does it finish with? This is the power of, so this is A, sorry, this is or to the power of 1, or squared. I'll just put in the next few, A or cubed, etc. This is T1, T2, T3, T4, etc. How many things do we actually want to add up? Remember, it's Sn. So we want to add up n things. So we want this to be Tn here. And what you'll see is that when that's 2, the power on or is 1. When it's 3, the power on or is 2. When it's 4, the power on or is 3. So when it's n, it's A or to the n minus 1. You just subtract 1 from it. Okay, so actually this is the thing that we're going to use, and we know that when we add those things together, that's Sn, which we're hoping to show is this thing here. So actually there is a bit of a setup to that one. That's not obvious at all. A or to the n minus 1, and we're hoping to show that it equals this. I'm just trying to buy myself a little bit more space, but I guess we're gonna run out of it very quickly anyway. So this is our to prove, really. Okay, to prove, because Sn is that thing. So we want to try for n equals 1. When n is 1, we get A or to the 1 minus 1, which is just A times or to the power of 0, which is A times 1, which is just A. So it tells us that we're starting with A there. And we let n equals 1 on the other side, we get A times 1 minus or to the power of 1 over 1 minus or. Well, 1 minus or divides into 1 minus or just to leave the A times 1 there. So we just get A. So it works for n equals 1. Next, we assume true for n equals k. So that is to say, we're taking it that A plus A or squared plus dot 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 plus A or to the k minus 1 is equal to A times 1 minus or to the k over 1 minus or. And what we want to do is we want to now say that if this is true, because it's an assumption, we don't know that it's true. If it's true, will it be true for n equals k plus 1? So that would just mean that A plus A or squared plus, we'll do our dot 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 there. A or, now in this case, k is going to become k plus 1, or n is going to become k plus 1. So remember, we're placing n equals k plus 1 into that thing. So it's going to be k plus 1 minus 1. That's just going to be the power of k. And it's equal to A times 1 minus or to the k over 1 minus or. Okay, remember the trick. We want to use this thing inside of there. We're saying that if it's true for a particular value, okay, will be true for the next value, k plus 1. So we want to use this thing in there. And the trick that we've always had, and this will be no different, is from this line here, put in the term. Hi gents, we're going to have a look now at some context and applications. This is again from sorry about that. Let's go for that again. Where were we? Yeah, we were just adding these things together. Yeah, show the second last term. So the second last term, obviously we're going backwards in ones for the power of or, so it's A or to the k minus 1 plus A or to the k, and shock r what we find is that this thing there is now that thing there, all bar the last one, the last term. And it's still equal to a times 1 minus or to the k over 1 minus or. So what we're going to do is we're going to replace this underlined red thing with what we said it was equal to. So we get 1 minus or to the k over 1 minus or. And it's going to be added on to now this thing here. I just noticed in order to be able to add them, a or to the k, in order to be able to add them, makes sense to multiply top and bottom by 1 minus or. Now everything is as it should be. Okay, don't multiply everything by 1 minus or. I know that's really tempting. Don't. It's just bad maths. Well, it's not bad maths. It's just not stylish maths. We'll say that. Just don't do it. Okay, we have here a times 1 minus or to the k plus a or to the k times 1 minus or, and that's all over 1 minus square. That's what that left hand side becomes. I'm not going to bother with the right hand side. Okay, is there anything to do? I don't know. Multiply out, I guess, would be the thing that strikes me. Yeah, there's nothing there, which seems like it's an easy way out. Okay, a minus a or to the k plus a or to the k. Well, that's good news. That looks like that's taking a dive. And it's minus a. Now, what am I doing this? I'm doing this thing here. It's a or to the k multiplied by minus or. Well, there's the minus multiplied by or, if you like that. So it's minus a or to the k, and that's or to the 1. And my rule is a to the m. Probably shouldn't use a there. As the example is a to the m plus n. So when we apply that, it's minus a times or to the k plus 1. So it's a or to the k plus 1. Okay, with that done, it's equal to that. This thing and that thing are nothing. So we get, sorry, this was all over 1 minus or, let's not forget that. So we get a minus a or to the k plus 1 over 1 minus or, and it's equal to something. We can factorize out the a's. Yeah, it's equal to a times 1 minus or to the k over 1 minus or. Did I do something a little bit silly there? I did actually, yeah, sorry, of course. Because when I was setting this thing up, beg your pardon, it was meant to be that we replaced k with k plus 1 or n with k plus 1. So that guy should have been that the whole time. So we'll just do a quick little amend on that. This is the nice thing, is that if you have forgotten just to write in the plus 1 or something like that, it won't work out, and you can just say, yeah, hold on, something's not quite right there. So we fix that up. And yeah, it does equal the thing that we want. So we can now say, there's that little really annoying spiel to write down. So we'll say that the truth of pk implies truth of p of k plus 1. Okay, and if we want to, we can kind of go back and just label what each one was. We call that proposition 1. Proposition, nope, we don't. Sorry, we go to actually where it is, proposition 1. This is proposition k. This is proposition k plus 1, just so they know which one that we're talking about. And just remember what I was doing there, that little thing that I should have done here was we go into k and put in k plus 1. So I've done it on the left, just not on the right. And of course, you got to do both. So this just says proposition k implies proposition k plus 1, meaning that if it's true for any particular value, it will be true for the next value. And we can say, since p1 is true, that was the first thing that we did. Just checked did it work for the first value of n, which is 1. Since p1 is true, we can now say that p1 implies p2, p2 implies p3, etc. Therefore, we can now say that a plus a or squared plus blah, 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 plus a or to the n, and minus 1 it was, yeah, is equal to a times 1 minus or to the n over 1 minus or. And you know what, it might be a good idea, since we know that that thing is Sn, and that is what they asked us to do. Save us writing an extra line out. Sn is that thing, and that thing is that thing. And a little QED, we certainly deserve a QED after doing all of that particular one there. Okay, whew. That was a lot of work, but I think we're okay. Derive from part 1 the sum to infinity of a geometric series where or is less than 1. Yet again, this came up in something that we were doing earlier, albeit that the question had something slightly wrong with it. In this case, what it's saying is or has to be between 1 and minus 1. And I actually mentioned in that video, though I'll mention it again, that if you take a number that's between that, let's say I took minus a half the last time, and if you keep multiplying it by itself, it's getting closer and closer to 0. So the limit of it is 0. So derive from part 1, so derive from what we just got, and we just got that Sn is equal to a times 1 minus or to the n over 1 minus or. We're trying to get the limit of this as n goes to infinity. We want to get what Sn is, basically. Okay, so we're just finding, or sorry, we're trying to find what's S infinity. So we're just doing the limit of a times 1 minus or to the n over 1 minus or, the limit there as n heads to infinity. Well, we just said if we have a number which is between 1 and minus 1, and if we put it to the power of 0, it is going, or yeah, put it to the power of infinity, it is going to head towards 0. So we can say that the limit of or to the n, maybe I just make this little note, if or is between 1 and minus 1, that's another way of saying that, that the limit of that thing is 0. I would just make that little note to my examiner. Look, I know what I am doing here. So if that is the case, what we would find is we'd get a times 1 minus, this thing is going to be 0 over 1 minus or. So we just get a over 1 minus or. So there we have it. We have S infinity is a over 1 minus or. So that's how you would derive that thing out. Okay, write 0.523232323 blah 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 in this form using that particular thing. So this is a neat little trick. So it means that it's 0.523232323, etc., etc., etc. And the way that you break this up is you should think of it as writing it as 0.5 added to 0.023 added to 0.00023 added to 0.0000023, etc. That's going to keep on going. So what we'll have here is we'll have 0.5, which we should just temporarily forget. And here what we have is a geometric sequence. Okay, we've got a geometric sequence because we're multiplying by a particular number to go from there to there and there to there, etc. So when it's a geometric sequence and we're adding them, it's a series, and it's an infinite series because this thing goes on forever. So a, which is the first term, is 0.023, or which is the next term. Now, what do you multiply to go from there to there? You know, it's easy when I tell you what it is, but one way to get this and be sure of it is you start with a particular number, take this number here, take this number here and divide it by the number that's in front of it. That is telling you what you get. If you think of it like this, you can write it as algebra, 0.02. You're going to multiply by a number. So multiplied by a number, we'll call it or, because it is or, and it's equal to, when you multiply by that number, you should get 0.0, sorry, I obviously killed off a 3 there. 0.023 times or 0, 0, 2, 3, 0, 0, 2, 3. Okay, so there you can see that you just divide 0, 2, 3 over 0 0.023. So you just take any particular one, divide by the previous one. That'll give you what the common ratio is right there. Okay, so if you want to, you could think of it as, I'm going to multiply top and bottom by a particular number. Maybe you could say, look, if we just go and look, you know, you should just be able to crack that one in your head, because obviously what's happening is the decimal place is moving over twice each time. So it's going to be 1 over 100. Okay, it's going to be 1 over 100. Essentially, you're just dividing by 100. It's the same as multiplying by 1 over 100. You can just type it into your calculator. We're just trying to save you the steps of doing it, but I suppose don't save yourself the steps whenever you are in the leaving. Just make sure that you're doing it right. Don't forget, there is a 1.5 out there. We'll worry about him in a second. So we're just doing this bit here. How many of these things are we adding up? We are adding up an infinite number of them. So we have that S infinity is equal to A over 1 minus R. So A is the first term, 0, 2, 3, over 1 minus R, which is 1 over that. So we get 0 0.023, and it's over 99 over 100. You can see here you can actually multiply top and bottom by 100 to immediately go to 2.3 over 99. Not that that's no, that's all that helpful, because you will just be using your calculator for this. So let me just type all that in, 0.023 over, and we'll just do our fraction, and it's 99 over 100. So we do end up with 230 over 990. That's, of course, just that bit in there. We have to add on a half. So if you just do plus 0.5, we see that it comes out as, so 230 over 990 plus a half. And my calculator is just saying 259 over 495. And if you just press the SD button, it comes up as 0.523232323, etc. So you know that you then have the right answer. Okay, and you can go from there. Okay, there was also a request just to do some palindromes. Maybe they'll do something weird about the fact that it's 2020. I would think that that's very likely now. It's worth just noticing that if it's a palindrome, this is not the same backwards as forwards. So you would end up with that. But they could of course do something like, you know, they could do the 2nd of February 2020, that being a nice palindrome that works in Europe as well as the US. So some sort of thing on palindromes could well come up. What I will do is we'll just maybe go to that vintage year that was 2002. So I'll just pause it here and get that for you first. Okay, and here we have, like magic, the 2002 paper here. So look, I can't really, you know, it's hard to anticipate what sort of palindromic questions they could ask. But here's just a way to, you know, practice and think about it and stuff like that. Okay, a palindromic number is one that reads the same forwards as backwards, such as that. This year is a palindromic year. When is the next palindromic year? So in order to have that happen, well, I don't know, you'd really just have to be able to see these things. Obviously, you know, 3003 might be the first instinctive thought that comes into your head. So it's that the two inner and the two outer have to be the same. Okay, if the two inner and two outer are the same, that's what you're dealing with. How many palindromic years are there from 1000 to 9999 inclusive? So in this case, you can just make a little list. Sorry, yeah, 1 1 1 1 1 2 2 1. Okay, and just do it like that. It'll come down to 1991. Going across the way, it was 2002. That also will make its way down to 2992. And it'll make its way over to 9009 and 9999. Okay, so if you see, we just have a box basically coming down the way. Each column has, be careful, each column has 10 things. There are 10 things going down the way. It goes from 0 to 9, 0, 1, 2, etc., all the way to 9. So there are 10 things, and going across the way there are just 9 things because it's going 1, 2, 3, all the way up to 9. So there are 90 years in between those two things there. Okay, there are 90 things there. If you want to, you can actually think of this as a box method. Might be a good way to think of it. Okay, how many options, how many numbers can fit inside there? So the numbers that can fit inside there, there are 9 numbers that can fit in there. But, as in, you can go 1, 2, 3, 4, 5, 6, 7, 8, 9. But the second you fill one in for there, in order to read the same backwards as forwards, you'll only have one option right there. So the next question is how many numbers could fit in there? And this bit is the tricky bit. It is 10. So easy to write down 9 again. But 0 is an acceptable number here. It's not acceptable in the other because suddenly you have a year which is below 1000. There are 10 options here. And again, once you set it in, the other one beside it has to be the same. So there will be only one option. So using our box method, there are 90 years that are palindromic that fit inside there. A whole number greater than 9 and less than 10,000 is selected at random. What's the probability that it's palindromic? So we're going to have to need to go from greater than 9, so we're 10 and above, all the way to 10,000 below, so that's 9,999. We have actually done some of that already. So let's just do, we should really look at the cases where it's 1 digit, 2 digit, 3 digit, because those are the boundaries. So 2 digits, well, that's easy enough. You've got 11, you've got 11, 22, 33, etc., all the way down to 99. So there are 9 options in total here. What you could have just said by a box method was that I have 9 options for this. I've only now got 1 option for that, so it's 9 by 1. Easy. 3 digits is a little bit trickier, so we'll just make our list 101, 111, 121. I think that's a good way to do it. Down to 191. And this also makes its way across 202, all the way down to 292, all the way over to 909, down to 999. Okay, going down the way, how many things do we have? We have 10 things. It goes from 0, 1, 2, etc., all the way to 9. So don't forget 0. And going across the way, we've 9 things as well. So there are 90 ways to do this one, and 4 digits we already got. 4 digits we also got was 90 ways to do it. Just to go back on that 3-digit one by the box method, 9 options to fill in here, only 1 there. Anything can go in the middle though, so you are going to get 90 via that method as well. Okay, so the number of ones that there are, the number favorable, remember the probability of any event is number of favorable over the number of possible. Number of favorable, add those together, 189. Number of possible, well, what are we choosing between? We're choosing between 10 and 9999. So how many numbers are between them inclusive, including both those numbers? That is a surprisingly tricky one. You will have to actually think about this, and just one good way, to do maths, just to get a little intuitive feel at the beginning, do with a small number. Like, what if it was 10 to 13? How many numbers are there between 10 to 13 inclusive? So there's 10, 11, 12, 13. There are 4 numbers. Might seem like there's 3. There are, of course, 4 numbers. So what you really want to do here, if you were to take 15, that would just be 14. 15, you can see that there are 6 numbers. So you might say to yourself, okay, yeah, I need to subtract that from that and then add 1. Okay, so 9, 9, 9, 9, take away 10 and add 1. So we do end up with 9, 9, 9, 0. That is the probability of that, of a palindromic year coming out of all of these ones here. So that's how many are favorable years. That's how many are possible if you were to choose at random. So that's just a palindromic one. Wouldn't shock me if that came up. Actually, it's topical, and well, it's topical in maths world perhaps. But that's one where you can sort of make up your own questions, like what date, if it's just day, month, year, like that, when is the next palindromic number. You could try to do something like that, just to maybe predict. That's high level prediction, but it's no bad idea just figuring out what sort of questions they might ask. Okay, gents, take care.